All right, guys, let's get started. Thank you for joining, those who have joined us on Zoom right now. And so, my name is Shabana, and I'm going to be talking a little bit about time series forecasting. And so, let's dive right into it. So, what we are looking at today as an outline, we'll talk a little bit about what is time series data, right? So, not every sequence data is time series data, and we'll talk a little bit about what makes the time series data and how you can define a time series data. We'll quickly look over the different types of time series data. Once we have done that, we'll look at different forecasting techniques. So we'll look at the definition and illustration of what forecasting actually means. Then we'll look at forecasting methods for stationary time series data, which is a type of time series data. And then we'll look at forecasting methods for non-stationary time series data. We'll quickly look at two deep learning methods as well. We'll look at RNNs, which are recurrent neural networks, and we'll also take a look at LSTMs, which are long short-term memory networks, to be able to forecast on time series data. All right, so what is time series data, right? I mean, we come across different time series data in our daily life. So everything from stock market to, let's say, if someone is looking at physiological data, so looking at heart rate variability data or looking at raw blood volume pulse or BVP data that's coming out from, let's say, your smartwatch. All of these things can be considered time series data. And so for data to be time series, it needs to be a sequence of data points. So X1, X2, X3, we've all seen that they need to be successive points in time, and preferably, there used to be a regular period or regular interval. Now, it makes our life very easy if we can find the periodicity of the time signal. But in most situations, that is not actually possible, and you're not able to find a periodicity for the time signal. So let's talk a little bit about what characterizes a time series data. So you have four different distinct characteristics that come into play when we talk about time series data. You have temporal dependence. What that says is that the values are not independent. That y of t is actually dependent on some previous value, y t minus n, right? And so that says that if you have a particular data point, it might be related to some data point in the history. It may not be related directly to a data point that is right before it, but it could be some other point, maybe 5 points before, maybe 6 points before, and so on and so forth. You have something called as a seasonality. A seasonality essentially is a periodicity or the time signal having a specific time period. So that could be something like seconds, that could be something like minutes, it could be hours, years, sometimes it could even be decades. If you are studying long time series, those could be over the course of years. And this always brings up an interesting question in if you have a time series that whose seasonality is in a decade or 10 years, if you look at a small chunk of it, if you just look at maybe 5 years of that data, you're not necessarily going to see those seasonality components in it. You're not necessarily going to see some of those low frequencies because for that to have a single period, you would at least need 10 years and not 5 years. So that's something to be mindful of when you're looking at time series data is to ask the question, how periodic is this data and how much of it do I need to look at to be able to do a basic analysis on it? Then we have something called as a trend. A trend is a DC component. So if you use the analogy of electrical circuits, AC, as everyone knows, is a sinusoidal alternating current, right? And those are your high frequency or low frequency components that are oscillating uh, around a particular mean. A DC component is something that's flat, has no oscillations, has no variability, has no frequency associated with it. Time series have a DC component, and what I mean by that is that they can have an upward or a downward trend, right? And this is very common in things like accelerometers. Accelerometers have a drift. So what I mean is that Even if the accelerometer is lying stationary on the table, its values might start drifting up slowly and steadily, right? We see trends and drifts in things like ECG. Every time somebody moves or when you have respiration artifacts, you can see the ECG signal as a whole keep going up and down. And those are what trends are. And they make it extremely difficult if trends are not removed to analyze time series data in a meaningful manner. And the final one is noise, which is the variability in the time series. And every time series is going to have some noise or randomness associated with it. This could arise from measurement defects to being an actual property of the system that we're trying to measure. So, a quick thought experiment. I have three different things over here. We have tossing a coin multiple times, rolling a dice, and something that is called a random walk. And a random walk essentially is a neck is when a time point depends on the previous time point plus some random noise added to it. And you could ask the question, are these time series or not? Because there's still sequence of data, right? I mean, you're tossing a coin multiple times, you're getting head, tails, head, tails, head, head, tails. You're rolling a dice and so on and so forth. If I put down the clock on the left-hand side, I could say I tossed my first coin at 12:01. I tossed my second coin at 12:02. Does that make this as a time series data or is it just a sequence data? So just because something looks like a sequence doesn't necessarily mean that it could be a time series data. In tossing a coin multiple times, those are independent events, right? So me tossing a coin the third time does not really depend on what the results of my coin toss were 2 coin tosses back, or rolling of a dice. These things are random events. These are independent events from each other. And if you remember, one of the core principles of a time series data was that the values had to be connected from within each other based on a value before them. Random walk, even though it is called random, is actually a time series data. It's right there where we say yt is equal to yt minus 1, where we are establishing the relationship that a output or that a value at time t depends on something previous to it. All right, so we discussed so far what a time series is. We looked at a few examples and determined if they are time series or not, or whether they're just sequence data. And now we'll look at the two main types of time series. So you have stationary time series and non-stationary time series. And stationary time series are the most simplest to work with. However, in real life, you rarely come across these things, right? And stationary time series are time series where the mean variance and autocorrelation are constant. And autocorrelation means how correlated a point in a time series is to its previous value. Fluctuations usually occur around the mean and the variance. And a good way to look at perhaps stationary time series is if I hold a string and if I pluck it, it starts vibrating. And it's vibrating around that mean if there was nothing to dampen it, if there was no there was no friction by air, if there was nothing, if the string was not actually losing energy in a perfect ideal system, let's say the string keeps on vibrating till a certain amount of time, that is fluctuating around a particular mean. A non-stationary time series essentially is the complete opposite. It has its mean change, which is basically what a trend is. We talked about a trend a little bit while back, the DC component. So when the mean of a time series changes, it appears like it has an upward or a downward trend, and that makes the time series non-stationary. Its variance changes. It has seasonality. Suddenly now there is a periodicity in that time series. So for example, you look at weather patterns, right? And you might have rain coming at the same time during the year. You might have the trend shift because of different reasons, because of global warming, because of other factors associated with it, but there's a seasonality associated with that time series data. So let's take a quick look at let's look at some examples of this. A few housekeeping notes as I'm talking about this. The code that was used to generate all of these examples, as well as some of the analysis, is in the new GitHub repository, which I'll put a link down in the Slack channel or hand it over to Carlos after the workshop. And what you see on the slides is where you can find the code in that Git repository. So this, for example, this was generated using the code stationary example.r. And what this is showing is just an example of a stationary time series. And the way it was generated was we took a periodic sine wave, which fluctuates around the mean. So it fluctuates around a mean of 0 and a standard deviation of 0.2. You can see that the variance is -1 and then 1. And then we had a mean and variance remains the same throughout this whole time series. This is really nice to look at. And to some extent, this is also easy to analyze and forecast using. And this is what we call a stationary time series. What you can see is you don't really observe any trend. The whole series is not going up or not going down. And that's why you say it doesn't really have a DC component to it. Let's take a look at example 2, which is a non-stationary time series. In this, you can see a distinct rise and upward trend in a time series, right? You see this often in stock markets. You might see small and high frequency fluctuations within a day, within an hour sometimes. But overall, when you apply a smoothing curve to it, you might see a trend from a week or 2 weeks back, right? And so trends are very common, and that's why non-stationary time series in the real life are very common. So for example, over here, you see a time series which has a trend of 0.05. We did simulate all of these data points, right? So we generated them so we know exactly what went into it. So we added a trend of uh, constant offset and then a slope of 0.05. We combined that linear trend with some random noise. That's why you see the jitters. And at the end of it, we added some seasonality to it using a sine wave. So you have all of these components mashed together to make that non-stationary time signal. And if you take a step back and just look at it, without analyzing this kind of looks random, but there is some sense into this, and we'll take a look at that in the future slides. But this is how most real-time or real-life data is going to look like. So let's start off with the first tool that we have. And the first tool that we have, given any non-stationary signal, is to try breaking it down into its principal characteristics, like we talked about in the previous slides. So breaking it down into a seasonality, into a trend, and then the remainder, which is just the noise or the fluctuations which remain after you take the first two out. If you are familiar with R, you can use a function called as STL, S for seasonality and T for trend, and L for losses, but I call it leftovers, right? And that's how you can remember the function STL. And when you apply that function to a non-stationary time signal, it outputs a couple of things. And I've gone ahead and plotted that output here. And so the first one, which just says data, that's showing you what the raw data actually look like, which is similar to what you have on the left-hand side of the slide. The second one is actually showing you the seasonality. And you can see that there was a sine wave that we had used for this particular simulated signal, and that's kind of coming out, right? But for example, if you had let's just say, particular stock market index or a physiological signal like a PPG or a heart rate, or maybe a day, maybe a few months, and so on and so forth. If you put that into this function, you would get a seasonality of how that signal fluctuates. And that right, that itself gives you a huge amount of value in understanding how the signal is performing. Because now you have the seasonality. Now you can apply all your frequency domain tools to it. You can apply FFTs. You can get the power spectrum. You can look at which frequency is most dominant in this signal. And if you have to do filtering, you can determine how to remove noise by different filter operations. The third thing it gives you is the trend. And it gives you a trend as a linear line, and you can see it right there. What it's saying is that this signal does have a trend, and it's an upward rising trend. And that's really important as well, because sometimes we don't really care for the daily fluctuations. What we care is the long-term trend. And that's pretty common in a lot of systems which go on for many, many months, for maybe a year, If you look at something as simple as grades, your grades might fluctuate on a weekly basis, but what really matters is your trend towards your GPA as it's going up in that direction. What is left after you remove all of this is the remainder, which is the noise that was added to the data, that was randomness that was part of this data, which made all that jagged peaks. That is what is remaining. So once you get this decomposition, it gives you a good idea. It gives you an idea of how non-stationary a signal is. It also gives you an idea of where you want to focus. Maybe the trend is not so important. Let's get rid of it. Maybe we only want to look at the seasonality. Maybe that answers the question itself because we want to predict when we might hit a zero again. And we have seen the seasonality trend across the years to be able to predict all of those things. All right. So a natural question that arises is how do you test for stationality or lack of it, right? The most simplest thing you can do, and I highly encourage you do this as the first step, is to do a visual inspection. And if you looked at these two signals, this one and then this one, it was pretty clear which one was non-stationary. This one was because you saw an upward trend. And in most signals, if you look at it, if you stare at it hard enough, you will realize that these signals are drifting up or these signals are drifting down, right? And there itself is your proof, or that itself is your hint that these signals are non-stationary. Once you have that, you can start decomposing the signal. So you can use the STL method. There's also a method called as decompose inside R. And so you could use both of these methods to be able to decompose the signal into its constituent parts, which is your seasonality, your trend, and then your error factor or the noise that is left after that. If you're not satisfied with the first two, you can use domain knowledge and don't ever rule that out because in most situations, we know the system, or even if we don't know the system exactly, we can approximate that the system that's generating this noise has some sort of a non-stationary element to it. And using that knowledge is very important as it allows you to justify all your statistical tests, but also what you're seeing. At the very end, I would say you can use statistical test. So you can use two commonly used tests to test for non-seasonal, non-stationary or stationarity of the signal. You can use an ADF test or you can use a KPSS test. Both of these can be found in Python as well as in R. I'll be walking you over some of the examples of using these tests and implementing them in R in the next few slides. So the ADFF test and the KPSS test, I'm not going to go into too much detail, but giving a high-level idea, these are essentially tests that give you a p-value, which means they're testing a null hypothesis and rejecting a null hypothesis. It's important to mention that the null hypothesis in both of these tests are different. So ADF test, the null hypothesis is that it implies non-stationarity. And the way for those who know what a unit root is, it does that by using unit roots on a stochastic process. But simply put, what it does is it checks for a linear trend and it checks for dependence on previous values. And if it says, hey, I found a linear trend, but I don't see a dependence on my previous values, then this signal must be non-stationary. That's your null hypothesis. So when you apply this to a stationary signal, and when you get a p-value, let's say of less than 0.05, your domain dictates what your p-value or the acceptable p-value is going to be. You go ahead and you reject your null hypothesis. To remind you, the null hypothesis was that it implied non-stationarity. And so if you reject the null hypothesis, then you're implying that the signal is stationary. The packages in R that you can use to determine this, the package is called tseries, and the function itself is adf.test that you can go ahead and use to run this test on time series data. The second test is a KPSS test, which is slightly more robust. Here, the null hypothesis is flipped. The null hypothesis for a KPSS test says that a signal is stationary. So if you get a p-value of less than 0.05 from this particular test, then you can reject your null hypothesis, which does imply that the signal is non-stationary. Again, you use the same package in R called tseries, and you can go ahead and use the function kpss.test to do this. Let's look at a few examples, and let's also look at a few imperfections in these tests. So the first example is the perfectly good stationary time series. You pass it to ADF, and it returns a p-value of 0.01. And that means we are rejecting the hypothesis and accepting the alternate hypothesis that this signal is stationary. In case of a KPSS test, you get a p-value of greater than zero point 0.1. That does indicate that this particular signal is also stationary. And similarly, over here for both the non-stationary signals, I do want to point out that over here, the ADF test actually gave you 0.03, which if we looked at just the p-values is less than 0.05, and you would go ahead and accept it. But the signal is clearly non-stationary, and that shows the importance of not relying on a single statistical test, because if you read up on these tests, they are meant to be used with very specific assumptions, and not all time series signals meet those assumptions. So it's always good to go ahead and use one or two statistical tests, but also visually look at that data and then take a guess of whether it's stationary or non-stationary. All right, so before we go into formally defining what a forecasting problem is, I want to specify why is it important to know if a signal is stationary or not stationary. And the reason for that is that it allows us to apply different tools to the signal based on what it is. So for example, the same way why you would need to know if a distribution is a normal distribution or not, because if it is, it opens up a whole different set of tools which have been vetted and have been used to then use on that normal distribution. Similarly, we can do the same thing if we know what time series it is. All right, so illustrating the problem. So what do we mean when we say time series forecasting? What we mean is that we have an unknown system which we can't see. Maybe it's behind a curtain, maybe it is invisible to us. We don't know what that is. And that's generating these different output points. And all we can observe is those output points. If we knew exactly the probabilistic nature of the unknown system, we could simulate those output points and we would not need to do any forecasting at all. So here the unknown the system is hidden, and we have a bunch of observations, and our job is to answer the question, what comes next? And that in a small nutshell is what time series forecasting is. So formalizing this problem a little bit more, xt is the data points. They include past values as well. So xt, t minus 1, t minus 2, and so on and so forth. You will often see this replaced with a y. And the reason for that is because once you start doing time series forecasting, what your yt value is was once your xt value, if that makes any sense. So you will see these two things used or written in a very interchangeable manner. H is your forecasting horizon, and you will see this a lot in literature as well as in R packages. They'll talk about forecasting horizon, even in Python packages. And that basically just says how far in the future do you want to forecast? So and the units depend on your time series data. So for example, if I am looking at, let's say, financial stock market data, I say H is equal to 5, maybe I want to forecast 5 days into the future, right? Intuitively, we can understand that the more into the future we want to forecast or predict, the worse those answers are going to be unless the signal is really, really seasonal, has some really good properties to it. You can't really forecast or predict that much into the future. L is what your lag factor is, and lag essentially means how many historic points in the past are you looking at. Sometimes you might only need to look at 5 points in the past. Sometimes you might need to look at hundreds of points in the past to make a model that is accurate enough to predict the future. The longer or the larger the lag value, and the more you look into the past, the more your model complexity increases and the more your computational requirements also go up. YT of clutch is YT of H, sorry, is essentially your future values added after the horizon. So YT of plus 1 is the next value in the future, YT plus 2, and then YT plus H is up till your forecasting horizon. F of H is your forecasting function, and we'll spend quite a lot of time talking about how to generate these functions and how to fit them. And UT plus H is your penalizer or your bias vector. And that essentially avoids or restricts the model from overfitting the data we are seeing right now and keeps some room for generalization of the model. Once you have fit a model, how do you actually determine if it's accurate or not? And you use that by calculating a prediction error. This is fairly standard. So what we are doing here is we are looking at the absolute mean between the predicted value or the actual value. We're looking at the residual error in the predicted prediction model. And we usually deal with two different norms of it. So we have an L1 norm and L2 norm. L1 norm is your mean absolute prediction error, and L2 norm is your mean squared prediction error. And you will see these two different loss functions used in a lot of different forecasting and prediction applications. All right. So let's look at a hierarchy, or rather a map of different forecasting options. And this is not even close to being exhaustive. There's a ton of different models out there. This just gives you a 1,000-foot idea of what to pick. So your models are generally divided into linear and nonlinear. If you're looking at linear models, you have autoregressive models, which I'm sure some of you might have heard about. Autoregressive models have things like rig regression, lasso, and things like that. Nonlinear models are divided into deep learning models, so RNN, which is your recurrent neural networks, GRU or GRU, which is your gated recurrent neural networks or gated recurrent units. LSTMs are your long short-term memory, and then transformers are what is fueling the whole burst of generative AI right now, which can also do probabilistic forecasting of data points. So let's take a look at some of the linear techniques first. And let's focus very specifically on stationary signals. And so the fundamental idea of an autoregressive model is it's regressing in on itself. So we all learned what regression is, right? And so in regression, you have an independent variable, you have a dependent variable. You're fitting some sort of a linear model onto it. You can also fit a nonlinear, or you can also fit a cubic model onto it, a polynomial model onto it, and so on and so forth, right? So you're trying to fit these different regression models. But in classical regression, you had a X and you had a Y. In autoregression, you are essentially fitting the model on its own previous values. So you're trying to fit Y on YT minus 1, trying to fit Y on YT minus 2, and so on and so forth. And that's where P comes in. P is the order of the model. How far do you want the model to look back, right? And that's what P is. And when you're reading literature, when you're reading books or documentation, you'll often find it being referred to as AR1, AR2, AR3. And all that means is AR1 essentially means autoregressive model with a P equal to 1. So it's only looking at one time step in the past. And AR5 would mean it's looking at up to 5 time steps in the past to create that autoregressive model. R is really easy to use here, so R can fit a really nice model to your data using metrics like AIC, um, or, and it can automatically pick the value for P for your particular model. I would suggest you can use a package in R called as forecast, and the method you can use is called AR. However, the method only allows you to fit to your data. It doesn't really allow you to forecast. And so you would have to write some P code manually. It returns the coefficients of the autoregressive model, but then you would have to write code to actually apply those coefficients to data. So I would suggest using a method called as auto.arima. We'll look a little bit about what ARIMA is in the future slides, but that automatically fits a complete linear model to your data set. All right. So let's take a look at what ARIMA is. And you can split ARIMA into three main components. So you can split ARIMA. Before we go into that, let's talk about why we need ARIMA. So we looked at autoregressive models. The simplest form of autoregressive models can be used for stationary signals. To remind everyone, stationary signals are those which have a constant mean and a variance. The statistical properties don't really change. Most signals in real life are not stationary, they're non-stationary, and for those signals, we can use ARIMA models. And if you break down ARIMA, the AR in ARIMA is autoregressive, autoregression. I is integrated, which is essentially trying to make the signal stationary, and MA is moving average. But be mindful, it's not the moving average you might think about, where you're used to having a window, you slide the window, it smooths the signals out. This is a slight different definition of moving average. So going top to bottom, we've already seen what an autoregressive model is. That's just showing a formal definition, is showing that you have a constant intercept. You have a summation function that's essentially has some parameters or the weights of the model, and that's how they determine what gets multiplied by 2 yt minus 1, and so on and so forth. And then you have a random, or you have a noise term, which is the epsilon term out there. I, which is the integrated, it takes an argument of a difference. And so what a difference is if your difference is 1, this particular step will take yt and subtract it from yt minus 1. So it's just subtracting successive points. If your difference is 2, it will do it twice. So it will first generate a signal of all the yt's minus yt minus 1. Then in that paired signal or signal of successive differences, it will do the same thing again. And the reason we are trying to do that is we're trying to make this signal stationary. We are trying to remove any non-stationary signals or non-stationary components out of the signal and make that stationary. And that's the reason why we're using this very important step called integrated. And that the parameter to it is the difference parameter, right? The third thing is your MA or moving average. And what this does at a high level is it captures a noise or random effect in the signal. And it does so by creating a model on the residual. So after you create your AR, your autoregressive model, you fit to a data, you find some residual errors. You can then go and look at the moving average or MA, and that is essentially trying to fit a model on those leftover residuals. What does this actually mean? It means it removes the short-term fluctuations or the shock effect, the ripple effect that's going through in the time series. And it starts making the time series a bit more pleasant, a bit more smooth to analyze. Combining all of these things together is what makes the ARIMA model. And every ARIMA model will have 3 different hyperparameters, the P, the D, and the Q. The P it is your lag for the autoregressive model. The D is the difference metric for your integrated step, and your Q is essentially the how far back you want to go into looking at your residual errors or residual noise. The good news is that R does all of this for you. So again, if you use the function auto.arima, you can actually fit to your data. You do have to, you can provide it with the PD and Q, or you can have R automatically calculated based on certain metrics. And once you have that, I mean, if you want to do it manually, you can use something like a grid search and try tuning the hyperparameters or looking at the domain and trying to figure out what could be the D to make this signal stationary. In most situations, it is probably 1, 2, 3, because when you start subtracting from successive values, the signal starts getting a little flatter in that sense, right? And then you can use the forecast method to actually go ahead and generate based on what you have fit to the model. All right. We're going to shift gears a little bit and we're going to go to a GitHub notebook, which I covered in the previous workshop when I gave this. And that will show you an example of using or operating autoregressive models, but using Python. So we looked at our methods, and now we're just going to go to the folks who love Python and kind of look at that as well. So let me switch over to that. All right, and I will also share this link right now on Zoom. If you go back on this Git repository, you will see you can go ahead and look at all the code there. There's also a notebook called as Tensors, a notebook named as Tensors. We're not really covering that. That was when I was talking about basics of PyTorch. So if somebody wants to learn how tensors work in PyTorch, they can go look at that notebook. And if you just replace the repository name from Data Lab Teaching Time Series to Data Lab Teaching Time Series 2, you will get all the material for today. So the presentation as well as the raw source code for the R and the figures that we used in the slides as well. All right, so with that, let's take a look at how to use how to build or fit an autoregressive model using Python. So this is just a problem definition, which I've already covered. You can read that when you look at the code as well. The data set that we're using is a simple daily minimum temperature data set. And you can look at the data set and you can immediately see that this has no non-stationary component. This is fairly easy. It has a nice periodicity. It's pretty stationary. It oscillates around a constant mean. You can look at that and you can see the mean is around 10. It has a constant variance up and down both. I think the mean is sorry around 15 or so, and then the variance is maybe 10 or 12 on top of it, both sides, but it's a stationary signal. One of the first things which I like doing when I have a time series signal is look at autocorrelation. And it's very easy to do that in Python. You can use pandas and you can use the method lag underscore plot. And that essentially plots a lagged graph. And what that is essentially doing is that it's looking at yt and it's looking at yt plus one. It could also be yt minus one, just how you name it. And it's finding a difference between it. So what it's asking is that what is the difference between the current point and the point before that, right? And ideally, you want a really high dependence. You want your current time series point to be highly dependent on the past one. And if you look at it that way, if you see that, you will see a nice little plot. You'll see a nice little point care plot right there, like I'm showing, which is really narrow and looks like a elongated football, right? And if you see that, then you know you have a really good relationship to, let's say, the previous time point in your series. You can also set the lag factor. And so over here, just to remind everyone, a lag factor is how back you need to look at in your time series data. And so you can set the lag factor, and here I'm setting the lag factor to 2. And it's looking at yt and yt plus 2, or yt plus 2 and yt, right? And you can see this, the graph is already starting to show some bulging in it. That tells me that the signal is not really that well dependent on even 2 points before it. That doesn't mean the signal is not dependent on a point that's 50 behind. It could actually be dependent on that as well. It just tells me it's not dependent really as good as the previous point on 2 points before. You can do the same exercise over here. I'm doing the exercise with a lag factor of 50. And the graph is really horrible, right? It just looks like a blob out there. And that's really telling me that there isn't really that much dependence that far back in the time series. You can look at that more numerically using the Pearson correlation coefficient. And the way you can do that is really simple in pandas is you can just use a .corr or .core or correlation method on your actual data frame as I'm showing here. I'm going to go ahead and make this big since I don't really know if everyone can see it. And then what you're seeing here is that it's trying to find out the correlation between T0 and the T minus 1, T0, T minus 2, and so on and so forth. And I can see that between T0 and T minus 1, there's a nice correlation of 0.7, but it's going down. It's going down to 0.63, it's going down to 0.58, 0.57, and so on and so forth, right? And that gives you an idea about how far back can you go and what your lag factor really can be when you're building your autoregressive models, but also when you're building your ARIMA models, right? Because ARIMA has the autoregressive part in it as well. This is also valuable when you're building your LSTM models that we'll talk about, because there's only so much finite memory, there's only so much finite resources that you can use to look back into time. And that's where lag really comes into play. Autocorrelation plot, you can use the function autocorrelation underscore plot. And what that shows you is it shows you what you saw in the table, but in a more graphical manner. And you see these oscillations, which are normal because your signal is also oscillatory. So your correlation is going from negative to positive, and so on and so forth. But what is interesting here and what is important is you see it start diminishing. And you start realizing that as my lag factor is increasing, my autocorrelation on those points is also going down. So you want to pick a data point that is computationally efficient on the resources and also gives you sufficient information to actually go ahead and build your model. And that could be a tunable hyperparameter in your model as well. Now, how do you fit these models? So we've gone through all of this. So in order to fit this model, you use a method called as autoreg, and that can be found in the stats model package inside of inside of Python, sorry, and you pass it the training data set, and you also pass it the lag. So how long before you want to actually look at it. I'm going ahead and I'm doing this. I'm also saying the metric I want to be able to test out is RMSE, which is root mean square error. And that's the metric that I'm going to look for as a comparison between the testing data set and the prediction data set. And once we have that, this is what the results look like using that method, right? So the blue is what I use for training, and the red is what the actual values of the signal coming next are going to be, and the green is what the forecasted values have been. They generally follow the same trend. They are quite good. However, they're not perfect. And as you can see that there's error of about plus or minus 1.2, which is my RMSE over here, which is what my error is. So if I spend some more time on it, maybe, if I clean the signal up a little bit, if I play with different lag values, we could try getting this better, but that will depend on your domain and how much you want to put in to improve your forecasting accuracy. Okay, now we're going to move back to our presentation, and we are going to start looking at the last part of this particular workshop, which is your deep learning methods for time series forecasting. So everyone has at least heard of, if not fully familiar with what neural networks are. So you have a bunch of hidden states which are automatically learned and trained. You have a set of input vectors, which is what the model sees, and then you have the model architecture that is, which determines how these different layers and different network or different layers are connected to each other. So on the left-hand side, you can see a very simple feed-forward neural network. It's a dense network where every input layer, every input neuron in the input layer, I1, I2, I3, is connected to your hidden neuron in the hidden layer, H1, H2, H3, and so on and so forth. What is different about a recurring neural network is that H1 not only depends on the input, but also depends on the output of the previous iteration, right? And so if you take that cyclic thing, you break it down and you kind of just sprawl it. It's how you will see in most of the textbooks, or that's how you will see on most of the online documentation. That's just showing you that the input for the current iteration is also the previous iteration. So there's some recurrence to this, and hence recurrent neural networks. What unfortunately happened is that recurrent neural networks were not really good at keeping track of long series and long sequences. And so LSTMs were formulated, which is long short-term memory units. And what long short-term memory units or LSTMs do is that they gate the input that's coming in, and they only let a little bit of it go back to the next stage. And we'll look at the detailed diagram of this here. And again, feel free to take screenshots, or you have this whole thing available to you as well. I am going to go over this in a zoomed way so I can kind of walk everyone over what this is. So the LSTM cell, and this is the LSTM cell, right? This becomes part of a bigger layer, a bigger network, and so on and so forth, has three different components. So you have your forget gate, which is right here. Let me try drawing it on the screen. So you have your forget gate, you have your input gate, and you have your output gate over here. The forget gate, what that does is you have your cell input. A cell input is a input from the previous iteration of this LSTM cell. And that's how it maintains that memory. That's how it maintains the long-term memory. So now you can have much longer lag factors of 50, 100, 200, and so on and so forth, right? And hidden state is the weights from the previous iteration. And so if you were generating a output every iteration, that is what the hidden state would be from that particular iteration, right? And so what's happening in the forget state is that it is using a bunch of operations. So it's using a sigmoid operation. Sigmoid operation basically takes the input and narrows it down between a 0 and a 1. It's using an additive operation between the previous hidden state and the current input, passing that to a sigmoid operator and essentially multiplying it or gating it with the cell state. And what this allows us to do, because sigmoid is 0 to 1, is that it tells the LSTM cell how much of the previous input it should actually pass through. And so if in its learning state, if it determines that it doesn't really need a whole lot from the past, it can start closing that particular gate, right? So it can start moving the weights towards 0, so it has less weight of what data is being passed through the cell state. Your input state is basically a combination of your input and HT. It does not really alter the state of the cell. So it's only concatenating it over here. And your output state finally is a state that takes the input, applies a tanh operation to it. A tanh operation, like I'm showing on the right hand side over here, is a nonlinear operation that takes any input data and buckets it between -1 and 1. And after that, you get a hidden output, and then you get the cell state, which can be used in the next iteration. So let's see how all of this works together. And let's take a look at an example notebook. Again, this is part of the GitHub repository, and I'm going to shift to that now. All right, this notebook is called as the basic LSTM. And let's walk over it on what we're doing here. So we're installing all the different dependencies that we need over here. Then we go ahead and we are using a data set from Yahoo Finance. We're using the Apple index fund listing, and we're using data all the way from 1990. So we have a decent amount of data that we're using. The different columns in that data or different fields we have available are the opening price, the highest price for the day, the lowest price for the day, the closing price, the adjusted closing, and the volume of trade that happened on that particular day for that index. The first thing you always do is visualize your data, because without that, you really don't know what you're doing. And so you visualize the data, and I can look at the opening price, I can look at the closing price across the life cycle of this data set, and I can start figuring out where and which one I want to go with, right? The next one is actually building out the training and testing split. So in order to be able to fairly judge the model, I want to keep some data aside for training. Around 80% of the data is what I've chosen to do right now, and then keep some data aside for testing, and that's the remaining 20% that I've chosen to do. I'm essentially just doing it. So in a time series data set, uh, unlike say any other data set, you can't just randomly pick data, right? Because they're dependent on each other. So I'm only picking the first 80% of the data for training and the last 20% of data for testing onto it. One of the drawbacks of machine learning models is a lot of pre-processing involved. And one of the important pre-processing steps is to be able to normalize the data. And so I'm going ahead and doing that. I'm normalizing the data between 0 and 1. Doing that to help with conversion, and also prevent different metrics who have different scales from unequally affecting the model. So if I bring everybody down between 0 and 1, those scales, unless you need them, the effect of the scales is diminished. I'm using the min-max scaler in Python to be able to do that. Once we have done that, in LSTM, everything has to be a fixed sequence. I do lie a little bit about that because you can use techniques like padding for variable length data, but padding essentially makes it a fixed sequence, and the input layer for LSTM needs to be a fixed sequence. So what we are doing in the next piece of code is we are taking our data and we are reshaping it into this form, M and K. M is the number of sequences. So for example, if I had 100 days of data, and if I've said that every sequence is going to be one day, my number of sequences will be 100. Data points per sequence. So again, 100 days of data, if my sequence length is 1, and let's say I have 1 point every hour, so that would be 24. I mean, that's not the case in this data set, but giving an example of it. And K is the features per data point. So for example, let's say I'm measuring somebody's acceleration as they're walking throughout the day, right? Those would be three, X, Y, and Z. So that's how you would generally structure your data as M and K in order to be able to feed that into the model. Next, we look at the model architecture. You can find further documentations in the links which I've attached there. And what I'm doing here is I'm creating a very simple LSTM layer, and I'm attaching a linear layer to it. And I'm attaching the linear layer or dimensionality of the linear layer to be the same as the outputs that are coming out from the LSTM. Oftentimes people get confused by this. It's the linear layer and the training is only occupied at the end. So when you think about iterating these models in your head, unroll these models out. And so if I'm going to iterate this model for a sequence length of 10, it means the model is going to loop through for 10. But to make it easy, if you unroll it in your head, so you make 10 boxes in your head, your final linear layer is applied to the 10th box. And then you can start training the whole model using stochastic gradient descent. Um, it's a modified version of stochastic gradient descent for these recurrent models, and that's what makes it so computationally intensive to train recurrent models with much larger sequence lengths. Once you have done that, you want to determine what your loss function is going to be. I'm going ahead here and determining the loss function to be a very simple mean square error or L2 loss. After that, you want to create batches. The advantage of creating batches is because the minimization can take place at a scale of batches rather than having it at every single data point. This speeds up a lot of computation. Plus, you can put batches into a GPU and have it work parallelly on that as well. This is a training and evaluation loop. And what this is doing at a high level is that for every data point, every sequence, it's creating a prediction. Then it's applying a loss function to the prediction, which is the prediction and the actual batched Y, which is the actual true. It's doing a backward propagation. So it is calculating the gradient, it is updating all the gradients in the backdrop of the deep learning step, and it is going and calling the optimizer step, which is the one that actually goes and updates the weights. It multiplies your gradient with the learning rate, and that's how you can start training your model. So we're doing all of that manually here so that when you look at the code, you can learn and understand what it's doing. This is just plotting for each and every epoch. Epoch is essentially how the iterations for how many times you want to do the whole thing again. And it's going ahead and plotting the error curve. And so I'm looking at the training loss as well as the testing loss. Once all of that is done, we can start forecasting it. And we can forecast it essentially just calling the predict or the model with the prediction mode on it. And we are appending the values as we are forecasting. So what I mean by that is, let's say today is Monday, I forecast the values of Tuesday, I append the values of Tuesday to Monday, and now I have Monday and Tuesday, and then I use that to forecast Wednesday. So I'm kind of like building the series, and I'm building and appending as I'm forecasting. Let's take a look at the results here. So the blue line shows the test data. The green line shows the actual data that was there. And then the red line shows the forecasted value. So I would argue that it's pretty good at fitting it over there. And then it's forecasting what the future might actually look like. This is an example of when it doesn't really work that well, right? And so it trained on this particular part of the model, and it thinks that after the training stops, there is a sheer drop, but that drop doesn't actually come way into the future. So what I'm trying to show with here is that, you know, these simplistic models are great, but, don't invest your stocks using these things. You're going to lose very quickly. And so be mindful of how you measure these models. They may work for some situations, they may not work for some situations. So it's always about exploring what's out there and what kind of different models might be used. In this situation, it actually does the forecasting quite well. So it fits the forecasted data. And then the rest of it, while it has the pattern, it doesn't really have the trend. So if you remember non-stationary signal, the DC component was a trend. For some reason, it doesn't think it's going to improve in that particular rate and things is going to improve in a much smaller rate, right? I talk a little bit about what these examples are and how you should interpret them. All right, guys, with that, I'm going to finish this off. We are at the end of the workshop. I hope you guys had a knowledgeable time and then happy to answer any questions on my email. Thank you.